that. So again, you have 2 sections due tonight, 4-1 and 4-3. On Saturday, you have 4-4, which we will lecture on today. You also have the review for exam 4 due on Saturday. It is worth points. It counts in as your homework. Don't forget you need to schedule exam form with ProctorU. You have to do that 72 hours ahead of when you plan to take it. So, and then you do have your peer reply to that second discussion on applications due also by Sunday. That's an additional 2 points out of the 10 points for each of those discussions. So that's what's upcoming. And of course the exam on Sunday. So, and then Sunday does mark the halfway point. Yay, we're halfway through our summer. So today we're gonna do section 4.4. I do apologize. I didn't get those notes sent out until like 9:30 last night. I had them all done and then I just spaced it. And at 9:15, I'm sitting there on the couch watching TV saying, I'm supposed to do something else. So I got them sent out. You can always go back and take a look at them once we've talked about them. So what we're gonna do today is build quadratic functions from application problems, basically. So everything we do today should end up to be an x squared or a w squared or something squared. So remember that in the back of the mind. So I've picked a variety of them. Yours are all very similar in terms of the homework. We're going to start with example 1. Example 1 says, a farmer has 200 meters of fencing and wants to close a rectangular plot that borders a straight highway. If the farmer does not fence the side along the highway, what's the largest area that can be enclosed? Okay. So I'm going to make a couple of notes to myself. So first of all, we want to maximize the area. So we need the maximum area possible. And that's what we're after. And so that means that I need to work with an area formula, which is just length times width for a rectangle. Okay, the next thing I'm going to write down is the fact that we know we have 200 feet of fencing. Okay, but fencing goes around the outside. It's not an area. That's the perimeter. And I'm going to leave a formula off for that for just a minute, and you'll see why. So I'm just writing down the information they gave me. The next thing we're going to do is draw a picture, because pictures always help here. So for us, here's my highway. The little dotted line down the highway. So there's the highway. And what we want to do is build a rectangle along the side of the highway, but we're not going to fence the side of the highway, which of course never makes sense from a practical point of view. If you were making a fence to keep your cattle in or whatever, wouldn't you fence the side by the highway? Even if it's a field of corn, you want to fence on the highway so people aren't jumping in and eating your corn. The reason we do it is a math point of view. It's got nothing to do from a practical word. So there's no fence on this side. Okay, well, at this point, we can start building things. I always like to label stuff, so I'm going to call this L for length. We're going to call this W for width. And let's talk about that 200 feet of fencing. So that 200 feet that we have has to cover the fence that we're going to put up on a plot of land. So how many W's and how many L's does that 200 feet of fencing have to cover? And that's what we're after here. So how many W's will I have?
2.
Yep. And how many lengths?
1.
Yep. Fantastic. And that's exactly it. So the reason I didn't immediately write a perimeter formula for a rectangle is because I knew that there were going to be some twists to it. Well, that's wonderful, but I nowhere see an x squared or a w squared or an L squared. I don't see a quadratic. This is a linear equation. And we want to maximize the area. So I'm going to leave this alone. I'm going to leave a little bit of space here. I'm going to come back in and write the area is the length times the width. This is the one that needs to be the quadratic because this is the one we want to maximize. We need a quadratic here. And again, the reason we need a quadratic is so we can go find the vertex because we know the vertex is going to be either a max or a min. So to do that, what we're going to do is recognize a couple of things in our background. If we want to write this as a function, then we can't have both L and W. We have to have one letter or the other letter. You can't have two. So what we're going to do is going back to this one and solve this for either L or W and substitute it. And that's our plan of attack. So it's easiest to solve for L because L has no coefficients. So let's just move the 2W over. So that's going to give me 200 minus 2W is equal to L. And now we'll substitute. So in place of the length, we're going to write 200 minus 2W and then times the extra W. So all we did was substitute in for the L. Very similar to what we did in section 3.6 last week. So that's then going to give me a function in terms of W that is, and what I'm going to do is distribute the W in and also put it in descending order so that it looks like our quadratics from yesterday. So that's a negative 2W squared, and then W times the 200 is going to be plus 200W. Okay. So we haven't gotten anywhere yet, really, but we've written a function, which is important. So again, we started off with writing down what they gave us. We drew a picture, we labeled our picture. We then wrote a formula using that fencing requirement that they gave us. Recognizing we need to maximize the area, we had to write an area function and get it into a single variable. Okay, now when you think about that, our quadratic that's sitting there is a negative 2W squared. So because our coefficient on the square term is negative, that's our A from yesterday, we know that this thing is going to open down. So if we were to graph this, this thing would do something like this. So we know it opens down. And because it opens down, we know it has a maximum, which ties in wonderfully with what we did yesterday. So that means we got to go find the vertex. So because we're looking for that maximum, we need the vertex. And that's why we had to do yesterday before we could do today. Okay, well, how do we go find the vertex? We do negative B over 2A. So for us, B is that 200. So that's negative 200 over A, which is a negative 2. So I have 2 times a negative 2. Well, that's, the negatives are going to cancel out. I have 200 divided by 4. That comes out to be 50. So I have a number, but I need to understand what that number represents. So what's really, really important here is to get a handle on what this function is saying. So if I come back and take a look at this and think about my picture, the only variable I have on the right-hand side is W, so that tells me that the horizontal axis is our width. Because we're writing this function in terms of A, that tells me my vertical axis represents the area. So this is the area, this is the width. So right now, this top is at 50 comma something. So that 50 corresponds to this axis, so this is the width. So the width of my field is only going to be 50 feet. So we now know back over here that this is 50 feet. Actually, I think I'm in meters. Yeah, we're in meters. So 50 meters. Okay, I'm going to step back and reread the question just to make sure I'm going to answer the question. So again, we've got 200 meters of fencing to enclose a rectangular plot. If we don't fence the side along the highway, what's the largest area that can be enclosed? So what they're actually asking for is the area. How am I going to find the area? I just found the width. How can I find the area?
Substitute 50.
Yeah. So let's take our 50 and plug it back into this function right here. So if we go and find A of 50, we'll get negative 2 times 50 squared plus 200 times 50. And then we go straight to the calculator and plug it all in. Be careful. Make sure you get that square in there. Make sure you get that negative on that. And if you do that, you should end up with 5,000 square meters. And that's our answer to the question. So we know that in terms of a plot of land, you can enclose 5,000 square meters. Is there another way I could have found that area? So because I tend to work without a calculator around, I could have come back over here to the length and figured out what the length was. So that would have been 200 minus 2 times the 50. So that's 200 minus 100, which is equal to 100. So that then tells me that that length is 100 meters squared, or 100 meters. And then I could have multiplied these two together. It just depends on which one you prefer to do. It doesn't matter. You're going to get the same answer both ways. Okay, so once we got our function written as a quadratic, we recognize that we need to find the vertex. We use the information we did yesterday about the negative b over 2a. You get the first coordinate of the vertex, and then when you plug it back in, you get the second coordinate of the vertex. So if you wanted to label the vertex back up here just to finish it, that would be 50 and 5,000. So. Okay, and for some reason, we all seem to like these farmer and fencing problems. So just so you know, it's a good application problem. When you hit your calculus class, whether it's the applied calc for some of you, that's the next course you'll take, or you take the theoretical calc, you'll see these problems again. Any comments about the first one?
I'm okay.
Yay! Okay, so example 2 kind of springboards off this idea of fencing a plot of land. So example 2 reads, a farmer has 1,000 feet of fencing. So this time we've got 1,000 feet to create a rectangular pen for his cows, and then divide the pen into 3 smaller equal-sized pens. So he wants to separate the cows out. What's the largest total area he can enclose? Let me read that again in case you didn't print it. A farmer has 1,000 feet of fencing to create a rectangular pen for his cows, and then divide the pen into 3 smaller equal-sized pens. What's the largest total area he can enclose? So we've got 1,000 feet of fencing, and again, we want to maximize, that would mean largest, our area, which is still our length times our width. Let's draw a picture just to get a handle on what's going on. So this time there's no highway, so we can draw a true rectangle with all 4 sides. Then he wants to come in and divide this. So we're going to start with this, and then we're going to divide it into 3 smaller pens of equal size. So I'm going to come in and draw in 2 inside pieces, then in order to divide it into my 3 pens, and they all have the same area. Now, putting the inside fencing doesn't affect the overall area, so my area truly is still my length times my width. For my picture, I always let the entire distance be the length, never split it up. It gets ugly with fractions. And then this side over here is still going to be W. Well, then that means that this is W, this is W, that's W. And why am I pointing that out? Because we now need to use that 1,000 feet of fencing and write an equation for our perimeter, or how much fence we're actually using. So that 1,000 is going to be equal to, well, how many W's do I see? How many W's am I counting up? Anybody?
Is it 4?
It
thought
is.
5. I just
No,
didn't
it's
know if
4.
the other side would be 5.
Yeah, because no, this side is this one, right?
Right.
So I've got 1, 2, 3, 4. Now this other side up top is another L. So how many L's do we have?
2.
Yeah, correct. And that's the key to the whole problems. Anytime you have a fencer, a farmer and his fencing, the key is to get the right number of W's and the right number of L's based off your picture. So, nice. Okay, we're going to leave that alone for a minute. We know that we're trying to maximize the area, which is going to be our length and our width. That does not depend on how many W's and how many L's there are. It's always just L times W. But again, the problem is that's got 2 variables in it, an L and a W. So we need to take our perimeter formula and solve for either L or W. So this time, what do you want to solve for? Which is still easier to solve for, the W or the L? Would you rather divide by 4 or would you rather divide by 2?
2.
Yeah, let's go solve for L. So we're going to move the 4W. That'll give me 1,000 minus 4W equals 2L. And then we'll divide everything by 2. So 500 minus 2W is equal to L. Then we're going to use that and substitute into the area. So again, just like we did in section 3.6, you solve for one variable and plug it into the other equation. So we now know that our area in terms of W will be, we'll pick up our L, that's 500 minus 2W times W. So again, we're taking this equation for length times width and just plugging in for the length. Distribute, put it in descending order just to make it nicer on us. So negative 2W squared plus 500W. There's our function. So again, thinking about it from a graphical point of view, the input value goes on the horizontal axis, that is still width. The output value goes on the vertical axis, that's our area. And A again is a -2, so we know that as a parabola, this thing is going to open down. I was going to do something like this. You can see that again, it has a max. It's really hard to find ones that have minimums, because in the real world, you want to maximize things, you want to make them as big as possible. The only time you really see minimums is when you're minimizing a cost function. So, okay, so we have to go find that max. So we're going to go do our -b/2a again. So that would be a -500 all over 2 times a -2. So that's 500 divided by 4, which comes out to be 125. And this time we are in feet. Now that's the width. And I know that's the width because it's the first coordinate of the maximum. And my first coordinate we're going to label with what the horizontal axis is. So it's the width. They actually want to know what the area is. So we'll take the 125 and plug it back in. So the area at 125 feet comes out to be a -2 times 125 squared plus 500 times 125. And then you go to your calculator. I'm going to let you guys do that. Does anybody have their calculator with them?
Yeah.
Somebody figure that out for me. It's not as nice of an answer as the last one.
77,629.
That is not what I got.
Nope.
Somebody else check that.
31,250.
That's what I've got. And that would be in square feet. And I think, Rich, that it's the negative that's throwing that off.
Yeah, that's where I messed up.
That's why I needed you guys to do it, because to see how easy it is to mess up that. So again, make sure you get parentheses and square before you multiply by the -2. So if we have 1,000 feet of fencing and we need to make 3 equal sized pens, the total area that we can close is 31,000 feet. So, yay, nice job. So again, in terms of steps, the very first thing you're going to do is honestly draw that picture. The next thing is to use the fencing to write a formula. And then you're going to do a substitution. So step 3 then is to solve for one of the letters. Step 4 is to plug it into the area function. Step 5 would be to come and do your -b/2a. And then step 6 is down here. And again, you can figure out what the length was by plugging it over here if you need to. So, okay, but now we're going to switch gears. So we've done 2 of those. You're going to do 2 of them, I think, on the assignment. Yes, you'll do 2 also. So, similar in nature. And then we're going to move on to a different type. Okay, so this is example 3. So example 3 reads, a parabolic arch, like an arch of rock, has a span of 120 feet and a maximum height of 25 feet. So the span, which would be this distance, is 120 feet. And the maximum height is 25 feet. So the directions say choose a suitable rectangular coordinate axes. I love that. And find the equation of the parabola. So they're giving me information about the parabola. They want the equation of the parabola. Then calculate the height of the arch at points 10 feet and 40 feet from the center. Let's deal with one thing at a time. So the first thing I'm going to do is draw my arch. Because it's a parabolic arch and they're talking about it like an arch in terms of either a bridge or in terms of rocks, something along that line, I'm going to open it down. We don't think of arches doing this. So what I'm going to choose to do is to put the y-axis right through the middle of it. And the reason to do that is because then this up here at the maximum height has an x-coordinate of 0 and a y-coordinate of 25. So it just makes the placement of that maximum, the vertex, up there fairly nice. So that's up there at 0, 25. Okay, the other thing we know is that the span is 125 feet. So the span is where the arch meets the ground on both sides. So that total distance is 120. So doesn't that mean that each side of this is 60? So again, take the 120, split it in half because of where I put the y-axis. So that gives me a point over here at 60, 0. So anytime I get a chance, I will always put the vertex right through the y-axis because it just works best. So how does that help me? Well, we're going to go back to what we saw yesterday. We know that one way to write the equation of a parabola is that formula. So that's the vertex formula I called it. So f of x is equal to a times x minus h squared plus k. That's using our transformations to write it in that form. Well, we know where the vertex is. We know that our vertex has an x coordinate of 0 and a y coordinate of 25. So I can immediately come in and replace h with 0 and replace k with 25. I'm going to clean that up because that's a little obnoxious. So that would be ax squared plus 25. And now we need to go find a. So again, a tells me whether it opens up or down, and in this case, I expect a to be negative because we're opening down. It also tells me about the width. So because this thing is really wide, I expect a to be a tiny number, so less than 1. So to find a, what am I going to do? Do you remember what we did yesterday? What do I do to find that a? So don't I have a second point that I could use? So if I plug in 0 for my y and 60 for my x, I should be able to figure out what a is. So to find a, we're going to use the second point, which is 60, 0. All right, so we just said the y is 0. That's going to be equal to a times 60 squared plus 25. I'm going to immediately move that 25 over because if not, I'll do something stupid with it. So, and 60 squared is 3,600. So 6 squared is 36, the 0 doubles, so I get 3,600a. So a is a really tiny number. It's negative 25 divided by 3,600. I went ahead and took it to a decimal. Because it's an application problem, you can use decimals here. So I'm going to move over here. I got a negative 0.00694, and I'm going to carry 3 decimals here because I have to give 2 more answers based on that. So I tend to carry a lot more digits than is necessary. But if you've taken any chemistry classes, you know that chemistry people care a lot about significant digits, and so do engineering, but mathematicians are kind of lazy about it. So we use what we feel like to use. So we'll use 3. Okay, so now we're going to have an equation of our parabola. So we now know that f of x is equal to that negative 0.00694 x squared. So what I'm doing is going back to here, plus the 25. So now if you tell me where you are in terms of an x, I can give you where the height is of this parabola. And again, this is only 25 feet tall, so 2.5-story building in terms of an arch. Okay, so part, I don't know, whatever you want to call it. They want us to calculate the height at 10 feet. So when x equals 10, we're going to plug that in. So f of 10 is equal to a negative 0.00694 times 10 squared plus 25. So in other words, if this is 60 and I'm only 10 feet over, how high is my arch? I expect it to be somewhat close to 25. Okay, back to the calculators. You guys do that and tell me what you get. My calculator's over here. Anybody?
It's a weird number I got.
Well, and it should be because this is a weird number. So I got 24.306. Okay, which should make some sense in terms of the problem. Again, the height is only 25 feet tall. We're 10 feet off the center. So we should be fairly close to the 25 feet. So I'm feeling good about that in terms of just logistics.
Okay.
Did you forget the negative again or drop a 0?
No, I put a subtraction sign instead of a negative, so it can't. So it followed
Yeah,
like
don't
the
do
answer
that.
prior.
Negatives,
That's so
negatives.
confusing.
And then they also want to know what it is at 40 feet from the center. So 40 feet is, 10, 20, 30, 40 is over here. So I expect it to be maybe half the size of that 25. I don't know. Okay. So, did anybody get that one? So I have 13.896. It's not quite half of it, right? Good. Hopefully that's what you're getting. Any comments or questions about that?
I'm okay.
Yeah, you guys are going to do one that's very similar. That's a suspension bridge. Now, on your suspension bridge problem, you're going to go this route with it, right? You're going to have that parabola open up, not down. So don't make your bridge look like this. It's a suspension bridge. It suspends the cable. So, okay, the next one's from the business world, and this is actually like the first problem on the assignment. This is really a short assignment as far as numbers go. I think there's only 6 maybe that you're gonna do. So there's not a lot of examples, right? But each one of them has multiple parts and they're gonna be a little bit more thought-provoking. Okay, so example 4 goes to the business world because this is one of the few places where we can pull out other applications of quadratics. It says the price in dollars and the quantity X sold of a certain product obey the demand equation. So P equals negative 1/3 X plus 100. So again, P is the price of whatever the object is, and X is the quantity sold. So this would be quantity sold. So it's how many of the things you're selling. And who knows what this object is? We're going to call it, I don't know, snowboards. I have no idea what to call it. So something that you're selling. Part A says we want to find a model that expresses the revenue as a function of X. And then because we haven't done this before, just to let you know that the revenue is equal to X times the price. And that should make sense. If you multiply how many you're selling times how much you sell them for, you're going to get your revenue. That's how much money you're bringing in. So if I sell 10 of them for $10, and I know I've got $100. So for us, all we have to do is a substitution because we need our revenue in terms of X, and X, that's equal to X times P. We're just going to substitute in for the P. So it's pretty straightforward. So in place of that P, we're going to plug in what the price is equal to. Well, now we can distribute. So that gives me a negative 1/3 X squared plus 100X. And that's R of X. So that's the answer to part A. They want us to write a revenue function. There's our revenue function. So that was pretty straightforward. Okay, part B wants to know what's the domain. Okay. Well, in order to get a handle on the domain, I'm going to think about this in terms of a graph. So this is X, this is the revenue in terms of X. Because of the negative and the 1/3, negative again means it's opening down. 1/3 means it's fairly wide. I know it's doing this. So does it make sense in the real world that you don't want a negative revenue? So what we're looking for basically is those 2 points. Those are x-intercepts. We know how to find x-intercepts. All we have to do is set our function equal to 0 and go solve it. So for part B, to find the domain, and that's only on this quadratic, right? We need the x-intercepts to find the domain. And then that's again because you don't want negative revenue. That's to avoid negative revenue. It is kind of goofy if you think about this from a business point of view, that at some point when you're selling more and more of that quantity, that you would end up with a negative revenue, but that's the nature of the beast. So, okay, well, let's take our quadratic, negative 1/3 x squared plus 100x, and set it equal to 0 and go solve that. Okay, so the first thing I'm going to do is divide everything by the negative to get it out of there. So that would give me 1/3 x squared minus 100x equals 0. So it just changes the sign on those two terms. Okay, let's go ahead and pull an x out of both terms. That'll give me 1/3 x minus 100 equals 0. So I've factored it, and I'm going to set my factors to 0. So x equals 0. 1/3 x minus 100 equals 0. That's a 1/3 x equals 100. And then multiplying both sides by 3 would give me 300. So I've just found the two x-intercepts. The one on the left side makes sense. If you sell, I'm sorry, yeah, if you don't sell any product, then you don't make any revenue. The other side is simply selling that anything above 300 that you sell is actually going to produce a negative revenue. So our domain then, to answer the question, is from 0 to 300. Now, I think it should have brackets on it. I'm honestly not sure what the MyLab is going to do with that. You may need parentheses there, but to me, from a logical point of view, 0 revenue is still a number as far as revenue goes, and so is 300. So I would include that. Okay, and that's the real reason why I picked this problem, is to help you find that domain. So, okay, part C. Yes, it goes on. It's got multiple parts. Part C says, what's the revenue if 100 units are sold? So R of 100, you just plug in 100. So that would be a negative 1/3 times 100 squared plus 100 times 100, and make sure I'm picking up the right function. Again, what we're picking up is this guy up here. That's our revenue function. Okay, and when you do that, I ended up with a weird number also, but that's that 1/3. So $6,666.67. So I'm just plugging it in. So this is saying that we know this is at 300. At 100, we're up here. So pretty good. Okay, part D asks us what quantity maximizes the revenue and what is the maximum revenue. So I finally see the word maximum. So the minute I see the word maximum in our class, we know we're looking for the vertex. So because they said maximizes, that's telling me to go find the vertex. Okay, so we know that's negative b over 2a. So we'll pick up a negative 100, put it over 2 times a negative 1/3. Okay, let's walk through this kind of slowly just to make sure we don't lose anybody on our fractions. So the negatives are going to cancel out. I'm going to drop them out of there. That would be 100 over 2/3. And then don't forget that when you're when you're dividing fractions, you multiply by the reciprocal. So that would be 100 times 3/2. Well, 2 goes into 150 times, and 3 times 50 is 150. Yes, you could have just used your calculator, but make sure you get a parenthesis around that denominator or you will get the wrong answer. So, okay, what does that mean? Well, again, according to our picture, this is the x-coordinate of the vertex. The x-coordinate of the vertex is the number that we're selling. So this is the quantity sold. So to get the most revenue, we need to sell 150 of our snowboards. Then what is the revenue? So then we would plug that back in to figure out the maximum revenue. And it better be bigger than the answer we got in the previous answer of the $6,666, because this should be larger than that. I ended up with 15,000 as my answer. So if you sell 150 snowboards, you will bring in a revenue of $15,000. That doesn't sound very impressive, does it? Maybe I'm a small business. Comments or questions so far? There's one more part to it.
I'm okay.
Okay. Part E then says, what price should the company charge to maximize revenue? Okay, well, the only place that we even talk about price is clear back up here in that initial equation. So the price can be found by P equals the negative 1/3 X plus 100. So we already know that X at the maximum was 150. So I'm going to pick up that 150 and use it to figure out what price I should be selling. So negative 1/3 times 150 plus 100. Well, third of 150 is negative 50. Plus 100 gives me 50. Okay, woohoo, there it is. So it's a really cheap snowboard. So if I make and sell them for $50, I'll sell 150 of them for a maximum revenue of $15,000. So your first homework problem is very similar to this one. The only thing that's going to change is that initial equation, which then changes everything from there on. So comments, questions? It's nice when they give you something to work from. Okay, one more. Okay, so example 5, the last one, says a rain gutter is to be made of aluminum sheets that are 14 inches wide by turning up the edges of 90 degrees. So if you've ever watched somebody put gutters on the house, they literally start off with a sheet of metal that's just a strip, and they literally run it through a machine that then folds the sides up, and they produce the length needed for the house. So literally, this is what they do. What depth will provide the maximum cross-sectional area and hence allow the most water to flow? Yes, I want the most water off my house. Okay, so the rain gutter is made out of sheets that are 14 inches wide by turning up the edges of 90 degrees. What depth gives us the biggest cross-sectional area? So again, you'll notice in there that we're looking for the max area. So we know that area is length times width again. Okay, so it really doesn't matter how long it is. What is going to depend here is that that sheet of metal is 14 inches wide. So it extends into the board, but is only 14 inches wide. So what we're going to do is we're going to come along and fold up the edges. So basically I'm going to make a kink right here and a kink right here, and then I'm going to fold that piece up and fold this piece up, and I end up with basically what looks like a rectangle. Now the top's open, right? This is open and allows the water to go into it so that it flows off the roof. Does everybody kind of pictorially understand it? It's really hard to take something that is three-dimensional and write it as a two-dimensional picture. The question is asking is how much do we have to fold up in order to get the most cross-sectional area and the most water to flow? So we're going to call these two sides X. So the piece that we're folding up, is that X? So literally I'm simply taking my piece of paper like this, and I'm going to fold it up like this. Okay, well, so our area is our length times our width. So I'm going to call this guy my length and this guy my width. So again, this side's the length, this side's the width. So the width's easy because it's just X. So I know that this W is really just X sitting at the end of this. But now I have to figure out the length. Well, I start off with 14 inches and I cut off X on both sides. So if I take that 14 and subtract an X on this side and subtract an X on this side, won't I get this inside piece? So isn't that 14 minus 2X? So we did a box problem last week, and that was kind of to lay grounds for that minus 2X this week. Okay, I did the hard part. Let's go ahead and put it in descending order, get rid of those parentheses. That would be a negative 2X squared plus 14X. There's your quadratic. Because this is a negative 2 sitting out in front, again, we know it opens down. It's doing this. So this is X, this is the area. And again, I know that because X is written on the right side, area is written on the left side. Okay, they just want the maximum area. Actually, they want to know what depth. So I'm going to come in and do our negative B over 2A. So it's a negative 14 over 2 times negative 2. That's 14 divided by 4, which does not come out even. I think it comes out to be 3.5. Yeah, 3.5. And this was in inches, so this is in inches. Okay, wait a minute. What the heck is that saying? So again, I'm going to go back to the idea of what this vertex is. So I know that it is 3.5 comma something, but they're not asking me for the actual area this time. They just want to know what the depth is. So what we're going to do when we go to make our gutter is we're going to turn up 3.5 inches on each side. So, and that answers the question. So again, the question is asking what depth will provide the maximum area? 3.5 inches deep. So that's how big, which is not very deep. It's about like that. It's about what a gutter is. So, okay, and that's the rain gutter problem. It's the farmer and the fencing problem in disguise. So just so you know, we ended and started on the same kinds of problems. Any trouble with that one? You're going to do one similar. The only thing that's going to change is the width of the piece of metal. It's the only thing that can change. Very good?
Yeah.
Okay, so the plan for tomorrow then is for review for the exam. So I have some problems already picked out that are similar to the ones you're going to see on the exam. You'll do another review in MyLab Math, so you get lots of reviewing for the exam. And that wraps up chapter 4. On Monday, we start chapter 5. So we're getting there. Slowly but surely, it feels like. Okay, any comments or questions?
Nope, I'm good.
I'm
Okay,
good.
we'll review tomorrow then. Have a good day. Enjoy it.
You too.
Thank you,
Bye.
too.